Part 4, we looked at the plots and determined what the differences were between colors on a plot. Now we can do some calculations. Now we're finally getting to your favorite spot, so here's where you can do that. Following is an example of calculating the difference numbers for a standard and a batch. Note, if you are subtracting a negative number, it is the same mathematically as adding that number. So if you haven't worked with negative numbers, if you want to subtract a negative 3, for instance, from 5, it's 5 minus the negative 3 is the same as 5 plus 3. So in that case, we'd get a value of 8. And raising a value to the half power is the same as the square root. 25 to the half power equals 5. Hopefully you know that 5 squared equals 25. Here's an example of two different colors, LAB numbers. We have our standard and our sample. We could calculate all of those values. If we look at these, start with the delta A. It's the A of the sample minus the A of the standard. 22 minus 20 gives us a positive 2. So that positive 2 delta A means that the sample is redder than the standard. Delta B, sample minus standard, negative 13 minus a negative 10 comes out to be a negative 3. So that means it's bluer. Delta L, L of the sample minus the L of the standard equals 27 minus 25, which is a positive 2. And that means the sample is lighter than the standard. Those are pretty straightforward and simple. Chromas for both of them, a little bit more involved. Not too hard, especially if you've got a calculator. We take our A and B values for our standard, which are 20 and negative 10. We square both of those and then add those together. So it would be 20 squared plus, and on your calculator you may want to leave out the negative on the 10. There's two ways you can do that and not screw it up. I've noticed that not all calculators, but some calculators, if you put negative 10 in there and square it, it'll give you a negative number at the end. Depends on the calculator. If you want to be sure, whenever you're square numbers, you can just leave out the negative. So you could take 20 squared plus 10 squared, or if you really are a stickler for details, you would have to do it this way. You would put a parenthesis, a negative, the 10, and then another parenthesis, and then square it. That would also give you 100 instead of a negative 100. So be careful on there. If you notice that the value you get is low, then you may have subtracted it. Anyway, you add those two together, 20 squared plus 10 squared, get a value, and you take the square root of that, and you'll get 22.3. So that's the chroma for the standard. Then you do the same thing for the sample, which would be 22 squared plus a negative 13 squared. Add those two up, take the square root of it, and you get 25.6. So to get the chroma, or the delta chroma, DC, the difference in chroma, you take 25.6, which is the C that we calculated for the sample, subtract 22.3, which is the C that we calculated from the standard, and we get 3.3. So that tells us that the sample is more chromatic than the standard. Delta E, then we take our delta A value that we got up here, which was 2, and square it. Our delta B value that we got above and square that, which was negative 3. And then our delta L value, which was also 2, square that. Add those together. So these numbers I can do in my head. That'd be 4 plus 9 plus 2. Add those up. That'd be 17. And then you take the square root of 17 and you get 4.1. That's the total color difference. And then finally, if we want to calculate the delta H, we have to start with our total color difference, the delta E, square that, then subtract out the delta L value and square that, and subtract out the C value, square that. So we have 4.1 squared minus 2 squared minus 3.3 squared, and we end up with a delta H value of 1.4. I'll give you examples of these that are written out. That's how you do the calculation. Fairly simple. A lot easier than doing the calculations, for instance, than calculating the absolute L, A, and B from the tri-stimulus values. I know as much as you'd like to do that, that's really not necessary. The computers will do that for you. And we can take those values and plot them on a absolute LAB plot. And here's an example of that. This is our LAB plot, and our standard was right here. So our standard is a positive 20 and a negative 10 for A and B. So that's our value. Our sample is a positive 2 and for A and a negative 13. That's where they fall on that. We can look at the graph now, and what did we say? We had a positive 2 for delta A, so we said it was redder, and it's confirmed here because it's to the right of the standard, so it's redder. We had a negative delta B, which means it's bluer, and that's what we said. And we said it was a positive delta C, so it's farther away from the center, so that confirms it. And we also said it was lighter, so it's above that. So those same conclusions come from either the numbers that we calculated or for the plot. Either one gives us the same information. It's just presented differently. The plot tells us the same qualitative information as the numbers. Like I just said, the sample is to the right of the standard, means the sample is redder or less green. The sample is below the standard, means its sample is bluer or less yellow. The sample is above the standard on the L scale, means it's lighter. Then here shows the chroma difference I mentioned. Since that line to the sample is longer than the line to the standard, sample is more chromatic than the standard. The two colors are not on the same line originally from the center of the plot. That means that the two colors are not the same hue. They have to be on the same line coming out from the center to be the same. And then this following slides show examples of the three most typical output screens from a color measuring instrument. It shows spectral curve, actual numerical difference numbers, and a color plot. These examples are from a Macbeth spectrophotometer and ProPalette QC software. We use these in our lab. These are very typical, one of the major manufacturers. And notice on the plot that the standard is in the center and the samples are placed relative to the standard. So the plot looks a little bit different than what we've been working with. What we've been working with has been what I call the absolute color space. This is a little bit different. So here's our spectral curve. This happens to show a standard in two trials. It shows the spectral numbers down on the bottom for the wavelengths of light and shows the different curves for each one of those. So that's what we can get from our spectrophotometer. Here shows the actual numbers. And this is the numbers for the trial here, the first three rows. And the differences are the three different illuminants, D65, artificial light, and cool white fluorescent. And you notice the numbers are different for the different light sources. And if you look even on the delta L, in D65 and fluorescent, the sample is lighter than the standard. In artificial light, it's darker. So that can happen. And then we see the values for A and B. And then we have another trial, and we have some different numbers. That's the output you can get from the spectrophotometer, and you can look at a couple trials right here. This is the same information that was on the previous slide for those spectral curves. And then finally, here's some color plots. This actually shows a different plot for the three different light sources. We have our D65 on the left, A in the middle, and cool white fluorescent on the right. And you can see they're a little bit different for each light source. The number 1 with a dot is sample number 1, trial number 1. The 2 is trial number 2. And you can see where they fall on our plots. The center point on all of these plots is our standard, and then the 1 and the 2 are our samples. So in all cases, our two samples are greener and bluer than our standard. This curve here represents the circle that goes around our center of our absolute curve. So anything on this circle, if they were on the same circle, they would be what? They would have the same what value? Hue, chroma, or lightness? Chroma. This line is the line coming out from the center of our point. So anything on this line would be same hue. Right. The way they show it, if it's a solid line, if it's down here, it's less chromatic. If it's a dotted line, it's more chromatic. So again, that information from the numbers would be the same as the information are on these plots. And this just shows one of them in a little bit more detail, where we have the lightness values here. So right here in the center would be the same lightness. Goes up that way, it's lighter, darker. Like I said, these are both bluer, greener. This one's closer to the hue. Number 1 is closer to the hue than number 2. And one thing about our screen, this always looks the same size. You have to look down at your scale here to determine how close you really are. So this is pretty far away since we're using tens. As you get closer, these scale numbers will go smaller and smaller. And here's one place where you do get the hue angle. Here, the hue angle is 43.86.